Welcome to lecture 26. Today we'll be covering the weak form Galerkin, and we're looking at the chapter 5 of my book, section 5.4. Again, there's other methods covered in the book that will not be covered in this course, but they are worth looking at. For example, you have the collocation method, the Petrov-Galerkin method, but in this course, we're focusing on three fundamental methods. The first one is called the Ryder-Ritz method, and the Ryder-Ritz method, you need the functional to be able to use it. And Ryder-Ritz, what it's really doing is solving the is approximating the solution to a differential equation or partial differential equation by minimizing the functional or maximizing the functional, minimizing if the functional is a quadratic of quadratic form. And then we discussed a strong form Galerkin. In the strong form Galerkin, what we learned about was that you can start from the differential equation directly or partial differential equation directly. And from there, you can then formulate an approximate method to solving it by creating a residual function. And that residual function is made orthogonal to the space of basis functions. And in the Ryder-Ritz method, we make sure that the approximation method is sufficiently differentiable in the functional, um, basically sufficiently smooth, that it satisfies the essential boundary conditions, that is complete, and that is the basis functions are linearly independent. In the strong form Galerkin, however, you have to satisfy the essential and um, not just the essential boundary conditions, but also the natural boundary conditions. Now, what is the benefit of the Ryder-Ritz method is that the Ryder-Ritz method, a lot of the problems that you encounter in structural mechanics, and you can actually take fluid flow problems, and you can also take electromechanical problems, and you can formulate a functional for them. The Ryder-Ritz method is very nice because you can apply the functional, you can apply the approximate method directly into the functional, plug it in, and then just minimize the functional with respect to the unknown coefficients. The weak form Galerkin, the strong form Galerkin, you have to start from the differential equation, is a little bit more work. But today I'll be covering the weak form Galerkin, where it's an improvement over the strong form Galerkin specifically. Is an improvement over the strong form Galerkin because in there is similar to Ryder-Ritz, where you only have to satisfy the essential boundary conditions of the problem. That's a very neat thing about it that has its benefits. So to then cover what this strong form Galerkin was about, took the differential equation and multiplied it by a function v, which I'm going to call it a basis function of some kind. And then I take the approximation to the differential equation, which is made by some pieces here. You have the unknown coefficients here. You have the basis functions here. And this one here is only here to satisfy the non-homogeneous boundary conditions. While the phis have to satisfy the homogeneous form of the essential and natural boundary conditions. You can see here that this has to be up to quadratic because if it was cubic, then when you plug it in here, it will vanish. And so that's not a really good approximation. Here, then we took the residual function and made it orthogonal to each of the basis functions. And there's n of them. So phi1, phi up to phi n. And here we plugged in the approximation for W, as you can see here, and you get n equations and n unknowns. And then you solve for the coefficients CI. And so that's where you will find those coefficients by doing this. Now you may think, what is going on here? Well, you'll get a linear system of equations, and that linear system of equations is going to look like this, with a vector column of unknown coefficient c. So c1, c up to cn goes up here, and then you have this vector here. So you invert this, and then you're able to get the c's very quickly. So very nice, very cool approach, very powerful approach. But there's some fundamental challenges with the strong form Galerkin. And the challenges is that it needs to be your approximation function has to satisfy a higher order of differentiation. And at a minimum, in the case I showed earlier, you need up to a third order or quartic polynomial to make sure it doesn't vanish in that integral. The approximate function also has to satisfy the essential and natural boundary conditions. That's also another disadvantage. That's not desirable because imagine if I have to impose all the boundary conditions, essential and natural, that'll make it really difficult to come up with an approximation function that can be used. And so it's not a preferred method, and finite elements really is based on the Riley-Rich or the weak form Galerkin. But the strong form Galerkin is important to understand because it provides the fundamentals on how where the weak form Galerkin comes from in the first place, and that's why I teach it is to kind of give that background. If you take in my finite element course, you've seen a lot of this material, but it's important to understand this course is different from the finite element course because in this course, we're not only trying to approximate the solution, we're trying to understand the fundamentals of calculus variations and how that applies to develop structural theories. And in fact, in this course, we'll be also talking about buckling and we'll be talking about a lot of other topics that are unique. In the finite element course, other things, other um, notes are not covered in this class. For example, dynamics and how to solve dynamic problems, and other problems of interest like fracture mechanics. So again, this course is really providing the fundamental that you need to really understand finite elements from the very uh, down to the core of everything. So very important. Here you have your partial differential equation in this case in a two-dimensional domain. And then here again, I multiply it by a function v, and I'll then approximate the solution by selecting a temperature um, approximation, and that will then be plugged in here, and then we'll then have a number of equations again. So here you can see that we plugged in T, the temperature approximation, and then you will then have um, n unknowns and equations because for each of these fees, you're going to select uh, these fees that make up the approximation. You're selecting the basis that makes up. It's called basis because those bases is what made up the approximation uh, that you selected. That's why it's called basis because that's the base. Those are the ingredients that make up the approximation. And what we're really saying here, I'm setting the residual function R. This is your residual function R. I'm making that orthogonal to each of the ingredients that make up the approximation function. So I get n equations, n unknowns. Again, I can solve for C1 up to Cn. But again, in this situation, I have to select a quadratic equation, for example, for me to be able to get a non-zero integral. Um, and so that increases the onus on trying to figure out what is the best approximation to the problem. Secondly, by selecting approximation of this method, uh, by selecting approximation for this method, you also have to satisfy essential and natural boundary conditions. That's not very desirable because that will make the problems even more complex. Just imagine if I'm modeling an aircraft and I have a wing, and that wing has lift loading. Imagine if I had to come up with an approximation to the solution that now has to satisfy the fact that I'm applying a lift load that looks complicated. Trust me, you don't want to do that. I want to come up with a method that can be easily be implemented, and that maybe all I have to do for the finite element then is to just specify the fixed conditions, and I have to make sure my approximation solution or my approximation function satisfy the essential boundary condition only. If I can do that, that'll be more desirable. Later on, we'll be covering mixed variational principles, and that method allows you to get a happy medium. And again, I haven't seen finite elements moved in that direction, but I think there's a lot of value in looking at that. So why we don't select an example again and kind of walk you through the variational principle using weak form Galerkin. So say you don't have a variational principle available. Say you don't have that. You have to start, say, with the beam equation. I apologize for that. We start with the beam equation again, and I'll just start with that, and I'll say, well, these are my essential boundary conditions to the problem, say, and say this is the yeah, that's the essential boundary conditions. I'll say that that this is let's just give it a value ei at w prime at 0. Let's just say I give it a moment of some sort, and then yeah, let's apply a moment on the other end just for fun, just to see what happens. And so what I'll do then, I'll now take this governing, when you have a fourth order differential equation, you should have four boundary conditions. So it makes sense I have four boundary conditions. Clearly, you know that two of them are essential and two of them are natural. But say you didn't know whatsoever what are the essential boundary conditions. You didn't know that at all. Um, the approach you want to use is to develop the idea of the weak form. And how you do that is by multiplying this, and it's similar to constructing a functional, which you're already seen, but I'll multiply by this by del W. That's the way, one way of doing it. And you can also multiply by V, but I selected del W because you can see much easier what's going on, since now you know calculus of variations. So I'll integrate this over the domain, and what I really done, I've taken this residual, look at this, I've taken the residual and plug it in here and made it orthogonal to virtual variations of the actual solution. Now I'm couching a little bit different because I want to bring it closer to what you learn about calculus of variations. We're making the residual function basically adjoint to the space of basis functions or the virtual variations. That's really what we've done there. And now the next step is really to integrate by parts. And my goal is to shift half of the derivatives over to these virtual variations of W. That's what I would like to do. And to do that, I'm going to take the residual function R, and I'm going to then shift a number of those derivatives uh, to the other side. Now, when you're using the weak form Galerkin or strong form Galerkin, you don't have to have a exact solution. Sorry, you don't have to have a conservative system. With Riley-Rich, for most of the cases when a functional exists and the functional has a minimum, the system has to be conservative. But when you're looking at this type of system here, where you start with the differential equation, the differential equation does not have to represent a conservative system. It can include damping, it can include loading, where the loading direction varies with the deflection, which makes it non-conservative loading. You saw one of the problems you working on Beck's or Routes columns. You should have seen that by now if you're working through the problems. You can also have a material that behaves inelastic. So this is very general and is very powerful. So then I'll move half of the derivatives over in this manner. And when I do that, I'll have triple integral there and then double integral there. And I move two of them over. You can see that happening. I move two of them and I'll stop there. I want to stop there. Now, there could be a situation where you have only uh, three primes. So if you were to have three primes, you just do your best to move the number of primes you can to the other, trying to keep everything by half. And that's just the way you do it. So here you have plus and minus, and then you have plus. And there's some interesting problem in the moisture diffusion world where you have an odd number of derivatives. And in those cases, you will just move um, enough to have about half. You won't be able to do it perfect, but you can just do the best you can. So the bottom goes now back into the integral, as you learned already from being an expert. If there's one thing you learn in this class is how to integrate parts both in 1D, 2D, and 3D. And we've even done it on 4D, by the way. You already done it for 4D if you haven't done it yet. One of the problems involved the time integral and integral of parts time integral. So you are a four-dimensional uh, integration of parts expert by now, which is quite impressive because I never thought when I took this course that I'll be an expert at that. So then I have minus q dx. So I'll complete, put it back into the integral, and then I'll then have the boundary terms plus ei w triple prime, and then I'll have this is at L. So I'll just plug in everything nicely. So it's very clear. And I'm doing it this way because I saw there was some confusion about how this works. So I'm making everything very clear for you so that when you go back and you study that, that is clear to you what is going on. And so With that said, I'll continue then integrating by parts very carefully. Oh, transferring all the terms over. I'm sorry about this. Uh, the computer is having a mind of its own, and we'll have to control it. There you go. I was able to write that at least. And then I have this term. And I advise that when you're working through all the problems, that you're very careful, step by step, everything very clear and clean. Now, you can see here, if I give you a differential equation and I gave you the boundary conditions here that I gave you on the right hand side, there's four of them, you can see. Um, this is very cool what I just done because I didn't know. If I gave you the differential equation and I give you the boundary conditions, you will have not known. Maybe you didn't know what the essential boundary conditions to the problem are, what the natural are. But now you know, once you integrate by parts, you can see that anything specified on W or W prime becomes your essential boundary condition. And you can see here clearly that W zero at zero is being specified as zero, or it could be a value. I could have given a value of W naught, but I gave it a value of zero. Regardless, it's specified. So you know this should go to zero because it's specified. And W at L is zero. So del W at that point is zero. So clearly that's zero as well. And then you have been given these values of EI here. So you can now substitute here what EIW double prime is, which is M at L, and this is M at zero. Okay. And then we still have to deal with this term and that term. And I'll explain how that's dealt with coming up. But we come up with a weak form now. This is called a weak form of the problem. You make this equal to zero, and when you call this a weak form of the problem, you will have arrived to this. If you took the functional and took the first variation, you will have arrived to this potentially. And you should know how to go from here to the functional as well, because we covered that as well. But the idea now is to substitute the approximation function for W. And the way you want to do this, let me write the weak form of the problem. This is a weak form of the problem. And the weak form of the problem has become EI, W double prime, del W prime minus Q dx. And then I have a number of boundary conditions, minus M at L bar, and then we have del W prime at L, and then we have plus M bar 0 del W prime at 0. And this is equal to 0. And so I want to kind of point a few things to you that you may not have realized, uh, but you're satisfying these boundary conditions implicitly in the weak form. So you're actually plugging in the natural boundary conditions directly into the equation, the weak form Galerkin equation. You may think, oh, if the approximate solution only has to satisfy the essential boundary conditions, then what is satisfying the natural boundary conditions? No worries. You're plugging in the natural boundary conditions exactly into the weak form, and we did it here. We did it right there. You can see it. So we are satisfying the natural boundary conditions the best we can. It's not going to be perfect because it's an approximation method. Now I'll take W and plug in an approximation for that. And I'm going to say it's going to look like this. And for any time you see del W, you're going to plug in. Anytime you see del W, you're going to plug in phi I. That's the way you're going to do it. Or phi J. Let's put phi J. That's the way this works. Here, I'm going to call this the weak form Galerkin, which depends now on W and del W, right? So that's the weak form Galerkin of the problem. And you can see here that for W, I'm going to plug in W tilde, and for del W, I'm going to plug in phi J and set that equal to 0. And then J equals 1 to N. And so when I do that, I'll get a set of equations again that's linear. You can get N equations and N unknowns, from which you can solve the CIs. Okay, so that's a process that we'll be following. I'll do one more example to kind of show you that process here, and we're going to do it with a heat conduction problem. Heat conduction problem, and you can even take the Navier-Stokes equation and do the same thing. Um, a fluid flow problem, we'll take that as this. So we're going to solve this problem here, the conduction problem here. And again, here we have AK, conductivity K, T prime, prime, plus Q, and Q is a heat flux, or the rate of heat. And prime here means dx. And I'll go through the same process again and construct the weak form. And the way I want to do that is to multiply this by del T, dx equals 0. And now what I'm going to do, I'm going to integrate by parts to bring the same number of derivatives on the primary variable of interest into del T. So I'm making the residual adjoint or orthogonal to the space of virtual functions del T, because this is really a virtual change in T. So I'm making that orthogonal against that. And hopefully that'll work. So then I'll take del T and I'll integrate parts very quickly here for you. And we'll do it in one step here really quickly. And plus and minus with very little pain. Very little pain, we get a lot done. And then I have this weak form Galerkin, and I like to call it weak form Galerkin so it's clear what I'm talking about. So when I said develop the weak form, just write this. I'm sorry. I should have said this. When I said develop the weak form, write it without the G. That's a weak form, and I apologize if I said that was a weak form Galerkin. This right here is the weak form of the problem. Weak form of the problem. Well, this right here is a weak form Galerkin because I'm approximating the solution by plugging in those values. So I need to be careful, and I want you to also be careful with the way you use the language. So weak form depends on X. Let me just make it clear what it depends on so that you know exactly how this works. This depends on the first variation of T. And that's going to be equal to the minus akt prime del t prime, and I have plus q dx, and I have the boundary term. And I'll just write it all in once instead of separating that. I did it because I think there was some confusion about what this line meant, but that just means minus evaluated this minus the evaluated here, and that's equal to 0. And now all you have to do is to see that del T is anything specified on T is an essential boundary condition. Here, T specified both at T naught and TL. So clearly, this goes away, and that's your weak form right there. Nothing more to do. That's a weak form. You're done. Now the idea is to come up with a approximation to this. And I already covered this, so I'll just give it to you again. But you're going to have a phi naught that takes care of the inhomogeneous boundary conditions. Um, and so the approximation looks like this. And then you can add more terms. A1 x to L squared plus or minus x over L. And then plus, I can add more and more terms if I want. It's up to you how many terms you want to add. The more terms you add, the more likely you will approach the solution. You can see here that this is your phi naught that we've been talking about, and you can see how this phi naught becomes either T naught or TL depending upon whether you evaluate at x equals 0. So for example, at x equals 0, you get T naught. At x equals L, you get TL. So clearly this is taking care of, that's taking care of the inhomogeneous because it's not equal to 0. These boundary conditions are not equal to 0. So that's taking care of that. And then while these guys, these phis are taking care of the homogeneous form of the boundary condition, you can see that x equals 0, that gives you 0 at this boundary, and that at x equals L, that's 0 at this boundary. So it's working out. It's doing the right thing. It's disappearing where it needs to disappear. It is working very well. And now all you have to do is to plug in T tilde in here and plug in For del t, you want to plug in each of the basis functions phi1 here and phi2 here. And so you're going to construct then, you're going to construct, I'll do it here in the corner. You can construct the weak form Galerkin, and there'll be n equations and unknowns, because for t, you're going to substitute t tilde, and for del t, you're going to substitute phi j from j equals 1 to n equations and unknowns, and then you just solve the problem. All this can be done very quickly in Mathematica. I already covered this week from Galerkin, so I'll just skip these slides and just go straight to an example so you can see what we're talking about. I'll just skip to the example. We covered all this, and if I'll go slow in case you want to do watch it in slow motion. So I'll go slow, and then you can go in the video and play it at 0.25x. So you can just see what was done, or pause the video and kind of watch it. Okay. I just did exactly, I already did all this. This is already shown to you step by step. And that's your weak form. That's your weak form right here. I was calling that WF earlier. And then here I was using V, but I like using del W. So V is the same as del W. You're making the residual. Let me go back. I was making the residual orthogonal to V, but I can make it orthogonal to del W. I like making it orthogonal to del W because if I teach this in a finite element course where I'm not teaching calculus variations, it's not clear what I'm doing. But now you guys know what I'm doing. I'm taking the residual, making it orthogonal to the change in W, which is virtual. And I think it makes more sense in this class to bring that up. But when you teach finite elements, you don't want to confuse people. I show this in a finite element course with no context on what calculus variation means. I think we'll have a significant issue. So that's why I can do that here. I'll go slowly so you can watch this slow motion. We already did all this. Okay, this is del W. This is del W prime. We already identified what the essential boundary conditions are for this kind of problem. Notice how I can derive this differential equation starting from first principles using calculus variations, using the principle of virtual work, and then I can develop the weak form from there. Very cool. Step by step. So this is your phi naught, that's your phi i's. You can put it in a vector format. These are your phis in the vector format. C is a column vector. Very cool. And then the natural boundary conditions, like I said before, are already considered implicitly in the weak form of Galerkin. Therefore, the approximate function only has to satisfy the essential boundary conditions. That's the only thing that's to satisfy. Only the essential boundary conditions. It has to be smooth enough. And look already at the progress I made. Look at the progress I made. These second order now. So my function, my approximate function, only has to go up to second order because I don't need to go cubic or quartic. I can just go second order. That's a huge benefit. If I use sine and cosines, of course, you have infinite number. It's always differentiable. So that's a good selection as well. Weight functions must also satisfy admissibility. We talked about that. Has to satisfy the homogeneous form of the essential boundary conditions. And you have to make sure that you're making that good progress. You want to make sure your function is continuous, doesn't have discontinuities. And yeah, quadratic function is a great choice. Why? Because I can construct this term. It doesn't go to zero, it doesn't vanish. It's sufficiently smooth. But if I was using the strong from Galerkin, I'm kind of stuck with the strong from Galerkin. The function's phi needs to be complete and linearly independent. Here you can see I missed a term. I did that on purpose, of course, to show you that I'm missing a term. So that's not good. This is a linear independent set. This is a linear independent set. And if you go at home, you will see that this is a linearly dependent set. That's not a good set of functions to be using. Why? Because I can write phi 3 as a function of phi 1 and phi 2. That's why. Each basis function has to satisfy the homogeneous form. Okay, so here's an example that I already kind of covered. You have several cases. You can have W specified at one of these boundaries, and this one I'm applying a particular rotation here. So that's non-homogeneous boundary condition. And I already went through this example. So we can skip this example. But again, you can go and pause the video at any point and see if you can get the same answer I got. But again, for W, you're plug it in the approximation function. And then for del V, del W or V, which is what I'm using in this particular set of notes, you can plug in the phi j's. And you can see here for the first equation, plug in phi I, phi 1, and phi 2 for the second one. Very nice. And then example 1b, here I'm applying a deflection here in this end. So it's the same thing. W at 0 is W naught, W prime at these locations, the slope is 0. And then here I'm applying a load here, which means that this term is non-zero, and there's no moment applied here at this end, so that's 0. And you know these are essential and natural. By constructing the weak form, you will find out. And you can see here that this is a good approximation. Why? W tilde at 0 is W naught. Perfect. W tilde prime at 0 is 0. You can check it. And you can see that it satisfies exactly this essential boundary condition. Very good. And then you may ask, well, where am I satisfying the natural boundary conditions? I show you. Right? So I have a good approximation function here. And then where I'm satisfying that easily, I'm looking at the boundary terms is where I'll plug it in. I plug in the minus p there, and then the rest of the terms will be 0. And you can check that at home and work it out. You can then do this in Mathematica very easily. No need to do anything by hand. Do not do it by hand. It's not worth it. This class is not trying to teach you how to do integrals or how to do derivatives. This class is teaching you the mechanics of how this works. And so just use a software that can do it for you. So perfect. I have the two equations, two unknowns, and then you just go ahead and solve it. And here I did it. I just plug in the first equation and the second equation. Equation number 1, equation number 2, solve for the coefficients. And then I have the approximate solution. I have the exact solution, and then you're ready to then plot it, and you will find that it matches. It will match very nice. I also can consider clamped elastic bar subjected to a distributed loading. And again, I have the differential equation with the boundary conditions. Here is fixed and here is fixed. So therefore the deflection is 0 at both ends. And you can see here that I take the differential equation, multiply by V, but I can multiply by del U. I prefer multiply by del U, but I borrowed these lecture notes from the finite element course. I just think it's cleaner when you do del U, because that way you can know what's the essential and natural boundary conditions, and you know exactly what's going on when you create the weak form. So I write it here in terms of del U, so you can see what it looks like. And you can see here that's my that is my um, weak form for the problem. And you can see what's the essential boundary condition quickly by doing that. And the point I want to make is that in our scenario, U has been specified on both ends here and here. So for this problem, I'll expect this to go to 0 at both ends. That makes sense. Um, and so again, in our problem, this goes to 0. This is your weak form here, and all you have to do now is come up with an approximation function that does that for you. And you can see here u tilde x is a great approximation function, because at u tilde of 0 you get 0, at u tilde of L you get 0, and your weak form Galerkin approximation, that approximation has to satisfy the essential boundary conditions exactly. has to satisfy this boundary condition exactly, and it does. You can see that here. So then the next step is very simple. Anywhere you see u, you're going to substitute u tilde, and anywhere you see del u, you'll plug in each of the fees, and clearly that's what we've done in this example. And then you get C1 from here. And that matches the strong from Galerkin solution. You can see here the strong from Galerkin, weak from Galerkin. And if you do the right rich on this problem, it will also be exact. Everything will match. And that makes sense because all the boundary conditions of the problem in this case are essential. The strong from Galerkin has to satisfy both essential and natural, but since there is no natural, then the strong from Galerkin has to satisfy everything. So that's why the weak form and strong form and right rich will match. So thank you very much for correcting me. I went a couple of slides back, and if you see here, Q is multiplied by del W, and I've forgotten to multiply that there, and also I forgot it to multiply here. I apologize for that. Pretty significant mistakes, but I'm allowed to do them. If you do them, you lose points, of course. That's why I took the class 10 years or many more years ago. I'm allowed to make the mistakes now because you cannot grade me. Um, so thank you for finding those errors. I appreciate for you being vigilant while we do this live lecture. Here we have the differential equation. Again, one more time, we have the differential equation here um, with these boundary conditions here. And what we've done, we've multiplied it by del u. And what we're really doing is taking the residual and making it orthogonal to the virtual change in this u here. Now, what you're really doing here, the virtual variations of u are really correspond to the adjoint space. And I showed you how to construct a joint, but again, this in the real scenario and this is in the virtual scenario. And what you're trying to do, you're trying to make the residual orthogonal to the virtual world, which is is adjoint to it. If the quadratic functional exists, then the virtual and the real become one, and so you have a self-adjoint. And I already showed you how to construct functionals and how to check for self-adjointness. In this example, again, I use V, but you can use del U. I think it's better to use del U, and that will give you the essential boundary conditions as being del U here. This V will become del U prime. This will become del U. Um, I personally think it's better, again, to be using um, um, del U. So multiply by del U, and things will become a little more clear. The approximation function only has to satisfy the essential boundary conditions. In our example, we can clearly see this essential and this natural, and I know that because I look at the boundary condition and I have a del u multiplied by u prime. So anything specified on u is, in fact, um, essential. And then u prime, clearly we can satisfy that implicitly with the boundary condition provided. And you can see here, then I have this approximation function I'm selecting, and a naught has to be one for me to have a good approximation function such that u tilde at 0 gives me one. You can see here is non-homogeneous, so it needs to give me one. And that's why I need that. I really need that phi naught to be one for that to work out. And then the rest of the terms are quite clear now. Nothing else has to be satisfied, simple. Phi1 is x, phi2 is x squared. And now for u tilde, I plug in all this. And then for the del u, I'll plug in each of the phis, x for the first equation, x squared for the second equation. You can see here how the phi here vanishes at x equals 0. That makes sense because these phis have to satisfy the homogeneous form of the boundary condition. That goes to 0 clearly at x equals 0. And then u tilde prime, this we know is 1, or I specified it as 0, so I apologize. So this is 0. You satisfy implicitly, that goes to 0 too. So you're basically done now. You have two equations, two unknowns, and you can now solve for C1 and C2. Um, And when you solve it, you get the two unknowns. You can do this in Mathematica very successfully. You can see how the weak form Galerkin matches the exact solution, and the strong form Galerkin will be a little bit more accurate because the strong form Galerkin has to satisfy the approximation solution has to satisfy both the essential and natural. That's why the strong form Galerkin here will be a little bit more accurate. But you can see that even with a quadratic equation, um, I was able to get really close to the exact solution. The exact solution is not, it's not, has e to the x stuff. So it's not like it's easy solution here. But yet with two-term approximation, we did great. I think it's amazing that we can even do this and even dream of doing this. Example 4 here now is examining the same example I covered last time, and notice how all the boundary conditions are now um, essential. So very similar from what we covered on the strong from Galerkin. And when you go about that, again, you integrate by parts. And here I didn't use index notation on purpose because it's useful to see what is going on sometimes. Sometimes when you use index notation, you forget why you're doing what you're doing. And I think it's just helpful to see things in a different way. And then you get, when you integrate parts, you will get a portion where essential boundary conditions are specified, a portion where natural boundary conditions are specified. But since the approximation function always has to satisfy the essential boundary conditions, just always go to zero. And the only thing now you have to make sure is that you can somehow satisfy the natural boundary conditions implicitly if those are given to you. In our problem, none of the boundary conditions are natural. So because of that, none of them are natural. That goes to zero. The essential are zero because the approximate function has to satisfy the essential boundary conditions exactly. So each of the fees has to be zero at each of the boundaries are essential. And so then I'm done. This is the weak form of the problem. And now I'm ready to substitute the approximation function, and I'm ready to substitute del u or v for each of the fees. And then I'm able to then go ahead and select an approximation function that satisfies the essential boundary conditions. You can see that's a very good one. You get zero everywhere on the edges of the rectangle. You also can add another term that works really well as well, and satisfy all the essential boundary conditions. You may say, "Oh, it's not good. It's not a good approximation because I skipped the term. Now I have x squared plus y squared." The reason is because when you look at the problem, it's a symmetric problem. So you should get symmetry to the solution about this axis, x and y. And so that's why this is a good approximation to the problem, is because it does do a good job of that, if you will. Um, and so from there, we could then go and use uh, the weak from Galerkin to do it in Mathematica. We don't go and pause the video and see how I did it. I don't want to dwell too much on this because it's actually very straightforward. You create the first equation, you create the second equation. Here I did it for one term, here for two terms, and again, within 0.5% of the exact solution. And I already covered the heat transfer problem by hand, so we can, you can pause the video. This one is more neat. This is with convection now. I like this one with convection. So multiply by del t. I did it with W, but you can multiply it by del t, and then your weak form becomes where you see del W, just call it del t, just for fun. So you can see that um, it's the same thing. And then here you can see uh, this right here is the weak form, which depends on W. And no, it depends on T and del T. Very nice, very nice. And that's how you set up the problem. That's it. Another problem could be you have multiple equations. So you have the first equation here, the second equation here, and it's subject to, say, these boundary conditions. So you want to use the weak form Galerkin with two unknown coefficients for each function. So just take the first function, multiply by v1, and the second equation by v2. You can also look at the higher order derivative, and that makes, you can make this del c, so multiply by del c, and then the higher order derivative on this second equation is W there, so multiply by del W instead of V1 and V2. You can do it that way as well. And you can even add the equations together if you wanted to, or you can keep them separate, doesn't matter. You integrate by parts to reduce the order here and bring half of it to the other side, to this one here. And I'll do the same thing here to bring the other half there. Very, very cool. And so now I have my two equations very simply. Um, and in these two equations, you can see the boundary conditions shown there. So now you want to satisfy that boundary condition, which is a natural boundary condition, directly into your problem. When you go through that, you will see that we need to enforce essential boundary conditions, implicitly satisfy the natural boundary conditions, clearly W at 0 is 0, C at 0 is 0, W at L is 0. So that automatically makes all the boundary conditions go to 0 when you look at this. So you can now select an approximation function that looks like this. That's pretty nice. And I selected W tilde like that because W tilde that way satisfies this condition and that condition. So at x equals 0, I get 0. At L, I get 0. So that's a good approximation function to select. Yeah, that's pretty much it there. And then for the second C, C only needs to satisfy the first one, which is that one, and that satisfies it, and you're done. So that's simple right there. Now you have four unknowns, so I have to have four equations. So all you have to do is plug in for the first equation. Plug in. Um, let me show you. So these are my two equations. So for the first equation, I plug in. Um, I'll show you. For the first equation, I plug in this one. Sorry, let me just mark it. Second equation. So this corresponds to the first equation. The equation in del C. And for the V's, you're gonna select the V. So for C, you're gonna plug in. I'm sorry again. So for C, you're gonna plug in C tilde. For W, you're gonna plug in W tilde. And for anywhere you see del C, you're gonna plug in the these basis functions here. This I call it lambda here instead of phi. And then for these two equations here, that's the equation in del W. Okay. So for that equation again, for C plug in C tilde, for W plug in W tilde, and then for del W plug in, and I don't remember what I called it. I call it fees. So we'll then plug in fees for that. And there you go. You have four equations, four unknowns, and you're ready to solve the equations using this weak form Galerkin. So the weak form Galerkin is an approximation method that forms the basis for the finite element method. The weak form Galerkin weakens the continuity requirements relative to the strong form Galerkin by integrating by parts. And the approximation function must satisfy the essential boundary conditions, while the natural boundary conditions are satisfied implicitly in the weak form statement. And then all examples show how we've done this. And I hope you're able to learn how to do this very carefully. And then we'll then move to a new topic. We've covered approximation theory in extensive detail. Um, Again, I started with the Riley-Ritz, where you need a functional, and it turns out with structural mechanics problems, a lot of them, you can construct a functional fairly simple. And then if you don't have a functional, you can start from the differential equation, or partial differential equation, start with the strong form Galerkin, has a higher order, a higher bar, a higher expectation, so it makes it harder to use for approximating solutions. Then you had the week from Galerkin, and we went through that, and it was really exciting to see how that works out. But for now, have a good day.